Dear students, today we will study about the remaining part of section 3.1, in which a simple loop in a uniform magnetic field is studied and the torque induced in a current carrying loop is considered. Then we will discuss another section, section 3.5 of the book, which deals with induced torque in AC machines. So we start with by production of induced force on a current carrying wire. As the current passes through a wire, a force is induced on that conductor or wire, and that force would be directly proportional to the current and length of that conductor, and there would be a relationship, as you can see in the slide. It would be L cross B, where L is the length of the conductor and B is the magnetic field which is going into the page in this slide. So if we find the cross product of L and B, the formula will simplify as ILB sine theta, and the direction of L is defined to be in the direction of current flow. So Fleming's right hand rule, as discussed in previous lecture, is quite helpful in finding the direction of F, L and B. If the index finger of right hand points in the direction of the vector L and the middle finger points in the direction of flux density vector B, then the thumb points in the direction of the resultant force F on the wire. Now we talk about the torque induced in a current carrying loop. Assume that the rotor loop is at some arbitrary angle theta with respect to the magnetic field, which is from left to right in this case, and current is flowing in that loop. If you see, the loop can be seen from top of it. Torque will be induced on the wire loop. To determine the magnitude and direction of torque, first the force on each segment of the loop is calculated. All the 4 segments of the loop are calculated separately, and then those torques are added to find the complete value of the torque. So the force is ILB as discussed before, and the torque would be perpendicular distance. This distance is from the point where force is applied up till the point where the loop is moving. the axis where loop is moving. So this distance would be called R, and F is that force which is applied at the given point. So R cross F would become RF sine theta. So we have four cases in which we will find the torque segment by segment. As you can see on the left diagram, the loop is shown from side view and top view in the presence of B. In the right diagram, you can see four parts, and in A part, the torque for the segment AB is calculated. In B, torque for the section BC is calculated. In C, the torque for segment CD is calculated. Similarly, the torque for DA is calculated in section D. All these sections would be discussed in detail in next slides. Now, first of all, we discuss segment AB. In this case, the direction of the current is into the page, while the magnetic field B points to the right, as you can see from the figure. The quantity L cross B points downwards. Therefore, the induced force on this segment of the wire is FIL cross B. So the ILB would be downwards. Similarly, the resulting torque is FR sine theta AB, and this is in clockwise direction, as you can see from the diagram. Now we talk about the segment BC. In this segment, the direction of the current is in the plane of the page, while the magnetic field B points to the right, as you can see from this figure, and the quantity L cross B points into the page. Therefore, the induced force on this segment of the wire is F is equal to I L cross B, and it would become ILB, and it would be into the page. And the torque in this case would be calculated as FR sine theta. But theta is sine theta would be 0 because theta is 90 over here. So in this case, it would become torque is equal to 0 in this case. Since for this segment the resulting torque is 0, since vectors R and L are parallel because both are pointing into the page and the angle theta BC is 0. So that's why the torque would be 0. Now we talk about the segment CD. In segment CD, the direction of the current is out of the page, while the magnetic field B points to the right. As you can see from the figure, the quantity L cross B points up. Therefore, the induced force on this segment of the wire is I L cross B in the upward direction, and simplifying this would become ILB. So the resulting torque would be F R sine theta CD and R ILB sine theta CD in the clockwise direction. Now if we talk about segment DA, the direction of current is in the plane of the page, while the magnetic field B points to the right. As already discussed in previous figure. The quantity L cross B points out of the page, therefore the induced force on this segment of the wire would be I L cross B, and ILB would be out of the page, and for this segment the resulting torque would be 0 since vectors R and L are parallel to each other, both are pointing out of the paper, and the angle theta dA is 0. So this torque dA would be 0. The total induced torque on the loop would be the sum of all the torques. Two of them were 0, but other two are RILB sine theta. Theta were different in both cases, but we know that both these angles are equal, so we assume that it is equal to theta, so we can write it as 2 RI LB sine theta. If we want to see the resulting torque as a function of angle, it can easily be seen in the sinusoidal diagram, which shows that at the time at the angle pi over 2 radians, the torque would be maximum, and similarly at pi it would be 0, at 2 pi it would be 0, at 3 pi by 2 it would be minus or you can say maximum in the minus direction, or minimum. The torque is zero when the plane of the loop is perpendicular to the magnetic field. The torque is maximum when the plane of the loop is parallel to the magnetic field. These two findings would be further simplified and discussed in coming few slides. From these two figures, it can be seen that B loop is also induced due to the current in the loop, where Bs is B because of the stator. The torque induced in a current carrying loop can further be discussed in the terms of induced torque, where 2RI LB sin theta can be written as 2RI LBS sin theta. The equation can be also expressed in terms of flux density produced due to current in the loop, which we have already discussed. This is called B loop. The magnitude of flux density B loop will be mu I over G, which shows that B loop is directly proportional to the current, and if we want to simplify the equation for the value of I, then we can find it that it would be equal to G over mu into B of loop, where G is geometry of the loop. But we know that loop, a rectangular loop, has an area equal to the height and the length, and if we say it length L into width, but width in this case is equal to 2R. Since we know that the width of the rectangular loop is 2R and length is L, the area would be 2RL. By putting these values, instead of 2RL we put A, and instead of I we put the value of the equation found on the left side of the column, and this, by substituting these two values, we find that it would be torque would be equal to Ag over mu B loop Bs sin theta. But this blue factor can be considered as K constant, and now if we see the equation, we come to know that there are in this torque there is a relationship between B loop and Bs, and the relationship between their angle between among them. K depends upon construction of the machine. Bs is the stator magnetic field already discussed. B loop is the B uh, developed because of the current in the loop. The torque equation can be expressed as a cross product, since we know that the simplification of cross product was B loop Bs sine theta, so it can be written as B loop cross Bs. The torque induced in the loop, and also in general the torque in any real AC machine, depends on four factors: the strength of the rotor magnetic field, the strength of external magnetic field. So this, in this case, if we see, one is B loop, other is Bs. The angle between the two magnetic fields, this is theta in our case. A constant representing the construction of the machine, which deals with geometry, in our equation, it is basically the constant K. The section 3.5, which deals with the induced torque in an AC machine. In an AC machine, under normal operating conditions, there are two magnetic fields present. One is the magnetic field from the rotor circuit, which is represented by Br, and another one is magnetic field from the stator circuit, represented with Bs. So interaction of these two magnetic fields produces torque in the machine, just as two permanent magnets near each other will experience a torque which causes them to line up. From the figure, you can see that a simplified AC machine with a sinusoidal stator flux distribution that peaks in the upward direction and a single coil of wire mounted on the rotor. The stator flux distribution in this machine is Bs alpha is equal to Bs sine alpha, where Bs is the magnitude of the peak flux density and Bs alpha is positive when the flux density vector points radially outward from the rotor surface to the stator surface. How much torque is produced in the rotor of this simplified AC machine? To find this, we will analyze the force and torque on each of the two conductors separately. So as you can see, there are two conductors. One conductor is showing a torque with a force with F induced 1, another is showing F induced 2. So we will conduct and find the force and torque separately. the induced force on conductor 1 is F is equal to ILBS ILBS sine alpha. If we find the torque, it would be R cross F, and if we further multiply with F, it will become R ILBS sine alpha. Induced force and torque on conductor 2. This is calculated by finding the force for conductor 2 separately, which again would be equal to ILBS sine alpha. Now the directions are shown in this figure. The direction for induced force 1 and induced force 2 are clearly induct are clearly shown in the diagram. So therefore the torque on the rotor loop would be summation of both of these two torques. One is the T induced 1, tau induced 1, another is tau induced 2. So the total tau would be summation of both of them, and it would be 2R ILBS sine alpha, which would be in counterclockwise direction. This equation can be expressed in more convenient form by looking at this figure and noting that the current I flowing in the rotor coil produces a magnetic field of its own. Direction of the peak of this magnetic field is given by right hand rule, and the angle between the peak of the stator flux density Ps and the peak of the rotor magnetic field Br is gamma. As we know that the tau induced in this case would be cross product of both of the magnetic fields multiplied with the constant K. The angle between the both of these magnetic fields would be gamma, and this can be simplified. The cross product will be opened and simplified in such a way that it would become KBRBS sine gamma in, and the direction of the torque would be counterclockwise in this case. But we know, as we already discussed in previous lecture, that theta is equal to 180 degree minus theta b or some other theta. So if we find the sine of theta 1, it would be equal to sine of 180 degree minus theta 2. In this case, we can say that gamma and 180 degree minus alpha would have the same value if we solve them for sine on both the sides. So that would be equal to sine alpha. So to simplify the previous equation, we say that torque induced would be KBR/BS sine alpha. But there is also another way to write this induced torque equation. If we need to write the equation in terms of BR and B net, then we find the value of BS from B net and BR as shown in the blue color. First of all, we find the value of this BS and put this value in the equation, and we get this induced torque equation. After getting this equation and multiplying the KBR, cross multiplying with this factor B net minus BR, we get the equation where one factor is KBR cross B net minus KBR cross BR. The second factor would become 0 because of sine 0. Tau induced would simplify by opening the cross product and multiplying with sine delta. So we say that the angle between BR and B net would be delta. So we represent it with uh, delta, and we say that if we open this cross product, it would become the magnitude of BR, magnitude of B net, and sine delta. The induced torque is a cross product of BR and B net, as we have already discussed, where delta is the angle between them. A simplified synchronous machine with its magnetic field rotating in the counterclockwise direction is shown in this figure. By applying the right hand rule, the induced torque is found to be clockwise, which is opposite to the direction of rotation of the rotor. Thank you.